Welcome! This week's lecture is on sample size calculations. I'm going to go through the details and examples given in the book and a little bit of a background about why this matters. This lecture aims to provide an overview of the concepts of power and sample size calculations, and I'm going to start with a bit of a review on the probabilities in relation to the normal curve so that you can understand the z-statistic which they include in the calculations, and they don't show how they go from the z-statistics to probabilities, which is why I'm giving this overview. Next, I'll talk about power calculations, the importance of them and how they're done, why that's in the book, and power calculations are also important and part of the concept behind sample size calculations. And again, I'm going to go through in this PowerPoint lecture the examples from the book. So here is a normal Gaussian curve. This is just a simple bell-shaped curve showing no skewness, and that means that with a normal curve, the mean and the median will be the same. So that means that 50% of the population will be above the mean and 50% will be below the mean. This also applies to probabilities. So when we do a calculation of likelihood of being above or below the mean or median value by a given number of standard deviations, we also talk in terms of probabilities. In the past, we talked about a two-sided t-test. So those were means comparisons where we looked at the probability of a 0.05 cutoff. So if you're talking about whether it's a t-test comparison or 95% confidence interval, when you're setting your p-value of 0.05 and it's a two-sided test, you're comparing how many people are above and below the mean by 1.96 z-scores. That is 1.96 standard deviations above and below the mean. And when it's a two-sided test for a 95% confidence interval, you'll have 2.5% above and below those cutoff values. So that means you have a combination of 5% probability of being outside of the 95% confidence interval and equally likely on the upper side as on the lower side. So this is the concept of the two-sided test where the p-value is set at 0.05. So we're using the z of 1.96 because it goes up until that 2.5%, so meaning that there's a 2.5% probability of being either above or below these values. But if it's a one-sided test, we use a different number. And that's because we're putting all of our eggs in that one basket on the right side of the curve. So we're using a plus 1.68 z-score or standard deviations above the curve to indicate that 5% of the population would be above that level and 95% of the population would be below that level. So in these calculations, when we're talking about a z-score or a z-statistic, that's the number of standard deviations above or below the median value. And what is the probability of being above or below that value? This is determined by the bell-shaped curve and can be looked up in a given table or as I give an online calculator. We're very interested to know the probability of both the type 1 and type 2 errors. Now the type 1 error, we haven't talked about it by that name, but we have talked about the concept that we have a 5% chance of making a mistake when we reject the null hypothesis and claim there is a statistically significant difference based on probabilities. And that probability level is set at 0.05. So in reality, we're allowing for the likelihood that 1 in 20 times by chance we will make a type 1 error. In other words, we will say there's a statistically significant difference when in fact there actually is no difference and that 1 in 20 times is entirely by chance. There's a second type of error, and that is the error of mistakenly accepting the null hypothesis. Now this is different from mistakenly rejecting the null hypothesis. That was our type 1 error. With the type 2 error, we actually conclude no difference when in fact there is a real difference. So instead of mistakenly rejecting the null hypothesis, we are mistakenly accepting the null hypothesis. And that means we're saying there's no statistically significant difference, but there really is a difference. The ability to avoid a type 1 error has to do with the power of your test. So power relates to correctly rejecting the null hypothesis, which is stating no difference, to accept the alternative, to correctly state there is a difference between these populations. And the ability to do that, to identify there is a real difference when there really is a difference, depends on what we call the power of your test. This table is about power and the probability of correctly rejecting the null hypothesis. Now, it starts with a column talking about the type 1 error, which you're familiar with already as being set at the 0.05 level. So that's the type of error we're capturing with our 95% confidence interval. So 95% of the time we will correctly accept the null hypothesis, and in 5% of the cases, we will incorrectly reject the null hypothesis. The concept of power is directly related to the type 2 error. And the type 2 error is when the null hypothesis is false, we actually accept it. So instead of stating that there is a difference, we incorrectly say there is no difference. And that's an error that we set at the beta level. And the power to correctly reject the null hypothesis when in fact the null hypothesis is indeed false is our power. So that is correctly stating there's a difference when there really is a difference. The power calculation will depend on the critical cutoff value, which very often we set at the 0.05 level. That's what we've been doing so far when we've been calculating 95% confidence intervals. It also depends on how much of a mean difference you expect to see and the variance in the population. So if you expect a larger mean difference, you will have more power. If you have a smaller variance, you will have more power. And if you shift your critical cutoff from a 0.05 level to a 0.10 level, you will have more power. What power calculations show us is that power can be increased by increasing the sample size, by the expectation of a larger effect estimate, such as a larger odds ratio, risk ratio, or a larger mean differences, or a smaller variance in the underlying population. A study is underpowered when the sample size is too small to show differences between groups or to stratify the groups. However, there is such a thing as a concept of being overpowered, and although that's not part of our analysis or it can't be tested statistically, that happens when every small difference you see is statistically significant. So if you have a sample size of 60, 80, 90, 100,000 people, sometimes even very small differences will appear to be statistically significant, and it's difficult to understand whether or not those differences are meaningful. The reason why power matters is that if a study is underpowered, then the sample size will be too small to show the differences that we expect to see between groups. It will also be too small to stratify the groups, and we will have wasted time and resources in setting up our study. So we need to understand the concept of power in order to design our sample size calculations. So here we're going to start going through some examples on power and power calculations and the meaning of power, and then proceed to the sample size calculations, which rely on setting a predetermined value of power. Okay, so here I'm going through the examples of the power calculations in the book. Here's the first example from the book. You can also find this in the Excel file where I've given in the sample mean, the variance expected, the mean difference, or actually the second mean value, which assumes a mean difference of 3. The assumption that the second population would have the same variance as the underlying population, and then the critical value of the alpha level set at 95%, and then the z statistic being 1.645, which is for a one-sided test. So plugging in all these numbers gives the z value of minus 0.476. Now, the power calculation is based on the power to detect a z greater than that value. So when we're doing the power calculations, we're looking to transform that z number, which we get from this formula, into a probability. So when you remember that bell-shaped curve, think of the number being on the left side of the scale, and our probability is going to be entirely to the right of that spectrum. So when we're looking at the power calculation, we have the z statistic minus 0.476. Now in the book there was a mistake. It was given as 0.470. But to go from a probability z to a probability, you have to use a table or an online site. And I'm giving the link for the online site that I use to convert the z statistic into a probability. Here is the online site that I gave the link for, and I'm giving the z number minus 0.476, and it comes up with a chance probability, they're calling it Q, of 0.317037. Now that is to the left of the z, so that's actually the probability related to your type 2 error. And your power is going to be the probability to the right of that, so your power is going to be 1 minus 0.317. Based on the previous slide, the probability of a type 2 error is 0.317, so that's your beta. And that's the probability of being less than or equal to z for the z value of minus 0.476. This result means that the power to correctly reject the null hypothesis when the alternative hypothesis is true is 0.683. And in the book, the wording that they use to describe that is the power to discriminate between random null hypothesis and systemic alternative hypothesis effects is 0.683, which is the probability of correctly rejecting the null in favor of the alternative hypothesis. The power to detect a difference in two samples assumes a normal distribution. So the second example that the book gives is how likely is it that a company with a level of 1.5 part per million will be detected as being above the safety standard for benzene when the cutoff is set at 1.0. So here is the formula for comparing the two means. So here's the example looking at the power to detect a mean difference of 0.5 parts per million benzene using 10 samples. Again, the mean that you start with is 1, that's the safety standard, and we're looking to see if it exceeds 1.5, if it will be detected. The 1.4 is the variance given, and the 10 is the number of samples that the authors decided to look for in doing their power calculation. And then you're looking for the z to identify your type 2 error, so that's your probability of less than or equal to z, and you're looking for your power, which is greater than or equal to z. So here is the formula filled in with all of the information given in the book. And we see that the power is the probability of being greater than or equal to 0 is 0.379. And if you want to double check that conversion from the z to probability, go online for the z tables or online calculators. That step is actually not given in the book. You can also do a power calculation for a relative risk. So here's the formula for a relative risk. Again, we're using the alpha cutoff of 0.05. And it depends on the number you have in your sample size. So that's the n value. And the p naught is the background probability or the proportion or prevalence given as a probability and the unexposed in your population. So we call that as the background proportion. And then your R there is your relative risk. So in your numerator, you need to have 1 minus r, so if your r is 1, that would be 0. But if you have an r that's 5, 1 minus 5 would be a negative number. And then you would have the square root of 5 if your r were set to 5. So there's a couple of things that the authors are showing here in this slide. This is a figure that shows power curves, the power to detect relative risks for multiple sample sizes. So they're looking to show the influence of sample size on power, but they're also showing the influence of the relative risk itself on power. So as you look at power, which is the y-axis, power goes up with increasing relative risk. You also see that the lines for the different sample sizes, so the line for 1,000 has a higher power all across the spectrum than the sample sizes for 500, 100, and 50. And that, of course, the sample size of 50 has the least amount of power, with stark differences for those with a sample size of 500 and 1,000. Now, power is important to the calculation for sample size. So far we've been able to calculate power, but we needed to have the sample size in order to calculate power. In order to calculate the sample size, we need both our alpha and our beta numbers. So we need to decide how much type 1 and type 2 error we're willing to accept in order to do a sample size calculation. So one sample test of a proportion, this is an example taken directly from the book, that's where you have two population proportions. So our underlying, our P0, population where the proportion is 50%. If we wanted to detect a 10% difference, then we would compare between 0.5 and 0.6. And the p-value given here is actually for proportion, and that is the average of the two population proportions. The two z numbers that we're giving are, one is for the alpha statistic, usually set at the 0.05 level, and the other is the beta statistic, which relates to how much type 2 error are we willing to accept. So we're only willing to accept a 0.05 type 1 error, that's usually the cutoff we use, but sometimes we are more lenient in how much of the type 2 error we're willing to accept. In this case, it's 0.10 or 10%. So this is the formula filled in for that one sample test of a proportion. And the value that comes out is a sample size of 212, filling in the details of the formula. So with a one sample test of a proportion, you can detect a 0.1 difference in proportion or a 10% difference in proportion with a sample size of 212. But now we take it to the next level, and that is if you have two samples and you want to test the difference between the proportions in the two samples. So just remember that with the sample size calculation, we're getting the sample size, or the n, for each of our groups. So given that it's a two-sample test and we have two groups that we're looking at, we'll have to multiply the answer by 2. So in this example, also given in the book, we have two proportions. In this case, the first population is 10%, the second population is 15%. The p-value in the formula indicates the proportion, which is an average of the two populations. And then the z-values given reflect an alpha type 1 error of 0.05, a beta type 2 error of 0.10. Those are the values that the authors decided to set. And then calculating with the numbers in the formula, you get 748. So that means for a two-sample comparison, you need 1,496 of total sample size. That is 748 in each of your two groups. You can also use a test of comparing two population proportions to get a sample size for an odds ratio comparison. So in this case, we're going to change the notation from population 1 and population 2, P1, P2, to looking at population exposed as being 1 and P0 as being the unexposed group. So typically you would know the proportion or the prevalence in your unexposed population. You would insert that into the formula as of probability. So if you have a 0.02, that would be a 2% prevalence and 0.02 probability. Then you, by putting in the odds ratio that you expect to find, you can calculate your expected probability or prevalence in your exposed population. So that's 0.058. And then from that information, you can calculate the P, which is the average of the two proportions or probabilities. And then the z-statistics would be set based on your type 1 and type 2 error, which the authors inserted as 0.05. So here is the sample size calculation worked out. That's a sample size of 567 per group based on the formula above. And because you have two groups, you're exposed and unexposed, that you're comparing, you have a total sample size of 1,134. At the end of the chapter, the authors describe how grouping continuous data into categories results in the loss of power. And they give the example of 100 observations. If 100 observations were necessary to achieve specific levels of alpha and beta, in other words, your type 1 and type 2 errors, using continuous data, you would then need at least 157 observations in order to get those same alpha and beta levels if the variables dichotomized. So this is just to demonstrate the degree of the loss of power. And as the mean differences increase, odds ratios become even more costly compared to a two-sample t-test. So what should you do if you have a continuous variable? If you're looking at a continuous variable and you're comparing longitudinal data over time, there are a couple of options you can use. One is to simply use a linear regression type of approach. So you can put many variables, your main exposure along with confounding variables, into a multivariate linear regression of exposure time or frequencies compared to some continuous outcome. Another option is to do t-tests comparing mean changes over time. So you can look at t-test comparisons by groups from the start and end times, or you can even do t-test comparisons at multiple time points over the time frame of your study. So this is a synopsis of the concepts of power calculations and sample size calculations, and some thoughts about looking at data that is continuous versus dichotomous, and the impact it has on your sample size and on your power. Thank you.